Okay, so there we go. We're recording now. I'm going to ask you to pardon me because I still have this lingering bronchial cough. So, analysis of variance, chapter 13. Analysis of variance has to do with it's a strategy or an approach that allows us to take a look at multiple populations and determine whether or not those populations have the same population mean, or whether or not there's a difference in at least one of those population means. Now, why would we be interested in something like that? So in a case, what if we were interested in whether or not all the counties in Nova Scotia have the same rainfall, annual rainfall, average annual rainfall? So in a case like that, we would want to test a hypothesis that they have the same annual rainfall or average annual rainfall. So we would have to assume that that is true, but now we want to find evidence that they do not have the same average annual rainfall. And so what we're looking for is at least one of those counties, Colchester, Halifax County, name it. We're just looking for at least one of those to be different. And if at least one of them is different, then we can reject the null hypothesis that claims all of those population means are not the same. Now, how should we go about conducting this test? What we've done before, we've done a test of hypothesis for a single population mean, where we make a claim about a population mean and then test that to determine whether or not that claim is true or not true, statistically speaking, of course. Then we moved on to two populations where we were interested in the difference between two population means, whether or not the means are the same or they differ. And now we're moving to three or more populations, sorry, not just three or more populations. And we want to determine whether or not at least one of those means differ. So we'll assume that they're all the same and then find evidence for them to differ. Now, one of the ways to approach this problem is to say, okay, let's take, if there are four populations, for example, let's take them a pair at a time. 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, and then 3 and 4. And see if we did pairwise comparisons, since we know how to do a test for the difference between two means, if we could do pairwise comparisons and we find a difference between the means, then in essence, in any pair, that is, at least one of those means would be different. But that's not a good strategy because, as I've just shown you there already, doing 1 and 3, 1 and 4, 1 and 2, that's 3 tests already. 2 and 3, 2 and 4, that's 5. And then 3 and 4, that's 6. That's 6 different pairs. And in each of them, there is a risk of committing type 1 error. So as you do multiple tests, you're compounding the problem, all right? So if you keep compounding the problem, then it's not a good and reliable way to test whether or not there's a difference between two population means. So we need to find another approach. What is that other approach? So that other approach is what we call analysis of variance. And I did have a short introductory video. If you looked at the course outline, and the very first video said a quick explanation of analysis of variance. So I'm going to try to give you a sense of that from the notes here. Excuse me. There's a picture that kind of explains this right here. So let's try to get this idea about how we would do this analysis. So one of the assumptions that we make is that the population, that essentially, if the means are the same, and we assume that the population standard deviations are all the same, then essentially, if the means are the same and the population standard deviation is the same, that is just a single distribution. It's not 2, it's not 3, it's not 4 of them, because if they have the same mean, the same standard deviation, then you superimpose them on each other, then it's exactly the same mean, same standard deviation, so it's the same distribution, same population. But it is possible to have the same variance, but different means. So we could have the same shape, that's where the variance comes in, but different means. So we could still make the assumption that the variances are the same, but then try to find evidence that the means differ. So if we look at the null hypothesis and we assume that it is true, then this diagram kind of represents what that should look like. In other words, there is a single population mean, and I'm just going to grab my iPad there for a second. In other words, there is this population mean that this population that you're seeing here, right? There's just a single population mean. And what we do is we take samples from that population. So if we're comparing multiple samples, because remember, what happened is that in analysis of variance, 3 or more populations, we would have 3 or more samples. And each sample would give us a sample mean, x bar 1, x bar 2, x bar 3, x bar 4, and so forth. So if the null hypothesis is true, and the means are the same, and the standard deviation is the same, then there's just a single population, and we just happen to have samples that came from that population. In other words, all the samples came from that population and gave us a sample mean x bar 1, x bar 2, x bar 3. We could even have a 4th one, x bar 4, right? So they all came from that, okay? And, excuse me, and even though those means look slightly different in the sense that when we take the samples, we will get some variation among the different samples. But it may not be enough that it questions whether or not it came from that single population. So if the null hypothesis is true, we will get those sample means, and those sample means will not be too far off this population mean mu. All right? So that's if the null hypothesis is true. But what if the null hypothesis is not true? Then we should have a situation that looks more like this, where it's possible that they all have the same standard deviation, but the means or the populations that it came from are different. And so what happens now is that you have, for example, a population here, mu1, and here's a sample that came from that population. Mu2, here's a sample that came from that population. Mu3, here's a sample that came from that population. But what you'll notice now is that those sample means are very far from each other. They're very different, right? So now, if they're spread out like this, there's a pretty good chance now that they did not come from the same population. Because if they came from the same population, the mean should be a lot closer. So analysis of variance allows us to look at the deviation between a mean, an overall mean, and the sample means to see whether or not there is sufficient variation between the different means. In other words, whether or not they're far away from each other, that seem to suggest that they could not have come from the same population. And to do that, we need a number of terms and formulas, all right? So a couple of concepts that we have to introduce you to be able to do that is as follows. First thing that we're going to want to introduce you to is something called an F distribution. So an F distribution. An F distribution looks kind of almost like a chi-squared distribution. F. So that's our final distribution that we will learn. And the F distribution is skewed to the right. And it's a distribution that is made up from the ratio of two sample variances, S1 squared, S1 squared over S2 squared. In other words, if I were to take two, if I took either two populations or whatever it is, but I have two samples, S1 and S2. Those are the sample standard deviations. If I take the ratio of those two standard deviations, or actually, sorry, the variances, because I have to square the standard deviation to get the variances. If I took all possible combinations of S1 and S2, then I get an F distribution. And what will happen is that if the variance of one is much larger than the variance of the other, so if S1 is much larger than S2, then I will find myself moving in that direction because that value here is 0, okay? And what happened now is that this distribution has two different degrees of freedom. Unlike the T distribution that we've used before, it has two different degrees of freedom. One that's associated with this sample, and the other one that's associated with this sample. And we call, if our sample size for the denominator is N2, then the degrees of freedom will be N2 minus 1. And if it is N1 for the numerator, it would be N1 minus 1. It's kind of similar to when we did a single sample T distribution. We said the degrees of freedom was N minus 1. So now we actually have a ratio of two variances and the two different degrees of freedom, and that gives us this distribution. So that's the last distribution we have to learn, and that distribution is called the F distribution. And so to use it, and I will show you how we use it, this is alpha, this is F alpha, but it has degrees of freedom df1, df2. Why do we call it df1, df2? df1 represents the numerator degrees of freedom, df2 the denominator degrees of freedom. So that's what we refer to those as. df1 numerator, df2 denominator degrees of freedom. All right. Excuse me. So let's see what that actually looks like, if we could find it here. So I'm going to just pause my share for a second and find that F distribution. Okay, no, I thought I had it set up for you already. Where is it? Okay, here we go. So if we go back to sharing, I should have the F distribution right here. Okay, so as you can see, it kind of looks similar to chi-squared, in that it looks kind of skewed to the right. And we have two different degrees of freedom. So if this is the area in the tail, then what happens is then we would find the F value by finding the combination of the degrees of freedom in the numerator and the degrees of freedom for the denominator. So in the top row here, that's the degrees of freedom for the numerator degrees of freedom you can see right here. And in the side right here on the side, we have the denominator degrees of freedom. So say, for example, I had a combination of 8 degrees of freedom for the numerator and then 5 degrees of freedom for the denominator. Depending on what area in the tail, is, we'll get the F value. So how do I know where to look for the area in the tail? That's this section right here, area in the upper tail. So if the area in the upper tail is 10%, 5%, 0.025, 0.01, all right, then we will find the corresponding F values. So for different areas here, we could find the F values. So when you're doing p-value, for example, if I have an F value, I would look up for the degrees, the combination of the degrees of freedom. I would look up that F value and see where it falls in terms of the area. Kind of like how you work with the t distribution, right? Except that instead of looking at one degree of freedom, one of the degrees of freedom for t distribution, just a single sample. In that case, we will be looking at 2 degrees of freedom. When I say 2, I mean the denominator and the numerator. We'll be looking at a combination of those 2 to find the p-value. So we'll try to get comfortable with that. Let's just take an example, another example. What is the F value if the numerator degrees of freedom is 10 and the denominator degrees of freedom is 4 and the area in the tail is 5%? So I would go numerator degrees of freedom 10, I'll come down here. Then I find denominator degrees of freedom 4. So 10 and 4. So I'm in this block right here. Area in the tail is 5%, so I gotta look at 5%, 0.05. And if I go across, my F value will be 5.96. So for 10 degrees of freedom numerator, 4 degrees of freedom denominator, with an area in the tail of 5%, my F value would be 5.96. So that's kind of how we use it. If I wanted to find a p-value now, and I told you, oh, my F value is, say, 6.1. 6.1, I'm just going to use that. But the combination in terms of denominator, numerator degrees of freedom, sorry, numerator, denominator degrees of freedom is 10, 4. So I'm going to use the same combination, 10 and 4. But my F value is 6.1. So let's look at that. 10, 4, and I'm looking for 6.1. I don't have 6.1. 6.1 is in between 5.96 and 8.84. If you look here, you will see that. So if it's in between those two, at 5.96, the area in the tail is 5%. At 8.84, the area in the tail is 2.5%, which means that when it is 6.1, the area in the tail will be between 2.5% and 5%. So that will be your p-value. P-value will be between 2.5% and 5%. And so that's kind of how you would use this F distribution. All right? So I wanted to make sure that we kind of get a feel for the F distribution in that regard right there. Good. So now that we've been introduced to the F distribution, let us try to understand the things that we need to conduct an analysis of variance. All right? We're going to need a number of terms. And so let us kind of take a look at that. I'll go back to my iPad. Okay, so number of things that we're going to need. And I believe we had someone just joined us. And so we were talking about analysis of variance for this class right here. So what we're looking at, just to kind of set it in context for you, and then I will give you the formula that we're going to need, and then we're going to work for an example, is that if, when we are looking at analysis of variance, it is really an experiment that involves comparing what we call, or it's an experiment where we are looking at a particular factor that we're interested in, and then there are different levels of that factor. For example, let's say we wanted to determine whether or not students perform differently in, say, different types of exams, marketing, economics, management science, and so on. So in a case like that, our factor is looking at exam performance. The different levels of that factor, or the different treatments, would be a marketing treatment of that, a management science treatment of that, an economics treatment of that, a finance treatment. So those will be referred to as treatments, right? And the factor really is your performance, your exam performance. And then we want to determine, for example, in that case, is the average performance different among the different types of tests, or are they more or less the same? And so if you could imagine what we would do in an experiment like that, is that we would take from marketing, for example, we would take a sample of test scores. From finance, we would take a sample of test scores. All right, let's call that in marketing, in finance. From economics, for example, econ, we could take a sample in E. We could do accounting as well. We could take a sample. The samples don't have to have the same size, but let's just kind of look at it. So what happened is that this came from the first one came from a population from marketing, population from finance, and we're trying to assess whether or not the mean performance, so mu marketing, mu finance, mu econ, mu accounting, whether or not those are equal. That would be your HO, that they're the same, equal to a constant value mu, or that at least one of them is different if the students don't perform the same on all of them. So that would be your HA, at least one is different. So how would we go about comparing that? I remember what I tried to show you a bit earlier is that if they came from the same population, then if I were to average, if they came from the same population, if I put all of the marks together across the 4 tests, if I pull them all together and I calculate an average, I'll call that average X double bar. What happens is that X double bar will be my best estimate of mu, the overall average that we want to estimate, right? Not estimate, but the overall average for that population that we said they all came from. But what will happen is that we will find our sample averages, which for example would be X bar for marketing, X bar for finance, X bar for econ, X bar for accounting. Those will be different spots here, for example, So this is our overall, and then these are your different means: X marketing, X finance, X econ, X bar econ, X bar accounting. So if they came from that same population, they really should be not too far from that overall mean right here. So we want to try to get a sense of how far they are from that. But what we would also like to do is to look at how far they are apart from each other. So if we could assess how far they're apart from each other and use that as an estimate of the overall variance compared to looking at each of them individually and then trying to estimate that population variance, we can get a sense of if those two things are very different. In other words, what it is that that same population that we believe that they all came from has a population standard deviation sigma. And what we're going to do is to use 2 approaches to estimate that. One is we're going to look at the difference between these sample means and the overall average and use that to generate an estimate. And then we're going to say, let us look at each of these individually. Let's look at the variation amongst the marketing, because not everybody in marketing got the same score. Let's look at variation among the finance exams. Not everybody got the same score. Let's look at variation among econ. Let's look at variation among accounting if we pull them all together and we get an estimate for that same population standard deviation, then now we have two estimates. All right? We now have two estimates for that same population standard deviation through two different methods. And what we want to do now is to see whether or not those two estimates are similar. And how can we measure that? We could measure it by putting one estimate, which we will call, later on it will become clearer, MSTR. For now, just ignore, I'll tell you where it comes from, over MSE. So one estimate which we will call MSE, let's say this is it, and the other estimate we'll call MSTR. And we will compare those. We'll compare those two. If the two estimates are similar, then it means that that ratio should be close to 1, and those samples came from the same population. But if the estimates are very different, if they're very different, because imagine two things that are very different trying to estimate the same value. So what's the explanation from that? Well, those samples did not come from the same population. That's a logical explanation, because if they came from the same population, the two methods that you're trying to use to estimate sigma should be reasonably close. They're not going to be exact, but because it's a sample we're talking about. But if they are very different, and how do we know if they're very different? What will happen is the ratio of one to the other will be much larger than 1 or much smaller than 1, but not close to 1. And so that's the logic behind all of this. So to do it, we're going to need some terms, as I mentioned. So let's get into some terminology. So the first thing we're going to know is because, oh, let me just go back here for a second. So the different exams, we're going to call them treatments. All right? The overall factor is exam performance. And the different treatments are a marketing treatment of exam performance, a finance treatment of exam performance, and so on, okay? So we have treatments. We have, so we will have variation due to treatments, which basically means the variation going between marketing, finance, economics, and accounting, the variation from the different exams. And then we're going to have the variation within each of the treatments. In other words, the variation within marketing, or the variation within finance, the variation within econ, variation within accounting. So we're going to call that the error variation. And then if we were to look at all the data together as if it is one big sample, we pull them all together, then we'll call that the total variation. So what we will do is we'll look at the total variation and make a note that the total variation is now made up of two parts to it. The variation because of the treatments and what's left. What's left we will call error variation. That's a term, that's one of the terms for it. And then remember that we're going to use that variation and the variation due to treatments to obtain two estimates for sigma. Okay. So here are some terms. Analysis of variance and completely randomized design. Why we say completely randomized design is because the samples that are exposed to each treatment is completely random. They're not the same people. So the people who took the marketing exam are not necessarily the same people who took the finance exam, not the very same people who took the econ exam, and so on. So we call it completely randomized design. Okay? So we have between treatments estimate of the population variance, as I mentioned to you, the treatments as we go from marketing to finance and so on, that's one estimate. Within treatments estimate, which we also refer to as the error variation of the population variance. So those are the two variations that we get. And then we compare them with what we call an F-test. And we create an Anova table. So we're going to need some terms. And that's the part that requires a little time. to kind of get used to. So the first thing we're going to do is to come up with what we call the mean square due to treatments. Now, what do we mean by a mean square? A mean square is essentially a variance. It's, in other words, it's the average of the squared values, and it's essentially a variance. Now, for you to appreciate that, we have to go back to when we first did standard deviation. Let me show you what I mean. If we go back to when we did standard deviation, way back in chapter 3, you remember we calculated S as standard deviation, or let's say S squared variance, as xi minus x double bar squared divided by n minus 1. That's variance. The standard deviation is just the square root of that. S is just the square root of xi, x bar. I said double bar. And by that time, we were not using double bar. It was just x bar. Add it all up. So divide by n minus 1. That's the standard deviation. So in essence, what we call this top is a sum of squares, SS, the squared values. You see the squares in the numerator? So we call it the sum of squares because we're adding things up. And when we divide it by the n minus 1, sum of squares divided by n minus 1 is a variance, S squared, sample variance. In fact, if you notice that the n minus 1 is the degrees of freedom that we use when we are doing the t-distribution. And that's just sum of squares. So in essence, a variance, I want you to keep that in mind, is a sum of squares divided by a degrees of freedom. All right, n minus 1. So if I go back, this here is my sum of squares. And the denominator will be my degrees of freedom. So in other words, that formula is a variance formula. But which variance is it? It's the variance between the treatments. And how do I know it's between the treatments? Look at what we've done. We took each treatment, which is column, we refer to columns as J, and we took the average. Okay, we took the average. And then we took the average of each column, so it gives us x bar j. We took the overall average of all of the values across all of the treatments, which give us x double bar. That means just add up all of the data together, divide by n. And then we weighted the squared difference by the sample size, and then divided it by k minus 1, which is the number of treatments minus 1. So in that case, I had 4 treatments, which is econ, finance, marketing, and accounting. So I have k minus 1, 4 treatments. So that here is a mean, it's called mean squared due to treatments, but another name for it is really just a variance due to treatments. All right? So remember what I mentioned to you, that what we're trying to do is to estimate the population variance using 2 different methods. If the estimates are close, it means that HO, we cannot reject HO. But if, and what is HO? HO is that the means are the same. But if the means are different, very different, then chances are they came from different populations, which means that we would expect the 2 estimates of the population variance to be different from each other. All right? So we see here the numerator is called the sum of squares due to treatments, denominator is the degrees of freedom. All right? And we get that. So now let's go to the within treatments estimate of population variance. So we want to estimate sigma squared, but now we're going to use within each of the treatments. So what we're doing is we're looking at the variation among the marketing students, the variation among those who took the finance exam, the variation of the marks for those who took econ, the variation of the mark for those who took accounting. So what we will do is we will get that variation, but we'll add it all up together. When we add that all up together and divide by in the total sample size minus k, that's the degrees of freedom here in this case. So that'll become a denominator degrees of freedom. Here, that's a sum of squares as well, but it's sum of squares due to the error. And the terms in here is the sample size for a treatment, -1, multiplied by the variance squared. So in essence, the top is still sum of squares, but the sum of squares due to the error term. And then this is the degrees of freedom due to the error term. So remember what I mentioned, that a variance is a sum of squares divided by degrees of freedom. So that formula we see right here essentially gives us another estimate of the variance, but is based on the treatments themselves, within the treatments. All right? Now, that numerator that you see here is these, and I want to show you why this is a sum of squares, all right? Now, let me show you why it's a sum of squares. Because we are using the sample size -1, which is just like n minus 1, and Sj squared is the sample variance. Let's go and take a look at this formula right here. Let's look at this formula. I will rewrite it. S squared is equal to all right. And what if I cross multiply? What do I get? If I cross multiply, this is over 1. So I'm hoping you remember cross multiplication. I will get that, and remember that this is our sum of squares over degrees of freedom. So I will get xi minus, I shouldn't have that, okay. So xi minus x bar squared is equal to n minus 1 times s squared. So look at that. N minus 1 times s squared is a sum of squares. So now if I go to this formula, I have the Sj squared, which basically just means the sample variance for column J, or treatment J. So for example, marketing or econ or accounting and so on. And the Nj minus 1 is the sample size minus 1. So when I multiply the sample size minus 1 times the variance, I'm actually getting a sum of squares. So what I wanted you to see is not that obvious, but that is a sum of squares here. All right? It is the sum of squares. Another way that we could rewrite this if we wanted to is to write it as x bar j minus x double bar squared. Right? X bar j minus x double bar squared. So x bar j minus x double bar squared. And let me see here. Yeah, that should give us x double bar squared. That there is the same thing. Right? That's the sum of squares. Okay, so we now have the denominator degrees of freedom, and it's right here. So now if we want to compare those two variances, we take the ratio of the two and then we measure it out. So let's look at this. So it says comparing the variance estimates, the F-test. If the null hypothesis is true and the analysis of variance assumptions are valid, and the analysis of variance assumptions, we need to know what that is, which is basically all of the samples are independently and randomly chosen, and that the population variances for the different populations happen to be the same. So if the means are the same and the population variances are the same, essentially we just have a single distribution, right? So the sampling distribution of MSTR, which is the mean square due to treatments over mean square error, is an F distribution. And we have the respective degrees of freedom. So in other words, we could use the F distribution to measure the ratio of those two estimates for us. Okay? if the means of the K populations are not equal, the value of MSTR over MSE will be inflated, will be overestimated, because MSTR will overestimate sigma squared. That means if they're far apart from each other, then it's going to overestimate sigma squared. And we'll have to reject the null hypothesis. However, if it turns out that the means happen to be from the same population, they happen to be equal, then in that case, we would find that MSTR over MSE is not a large number. In other words, they will be closer to 1, and we cannot reject the null hypothesis that those treatments have the same mean. Okay? So I think it's time to get into a problem. But before we get into that problem, one of the things that we should keep in mind is that when we're doing the analysis now, when we're going to do that analysis, we need to develop what we call an Anova table, analysis of variance table. An analysis of variance table allows us to summarize the data that we need for the analysis using this nice table right here. So what we will identify is what are the sources of variation. Sources of variation, in that case, would be the treatments and the error. The sum of squares, SSTR, sum of squares due to treatments, sum of squares due to the error. And if we add them up together, we'll get the total sum of squares. The degrees of freedom, K minus 1, N minus K, it says NT, which means the total. That means across all of the treatments. And then the ratio of SSTR to the degrees of freedom, SSE to the degrees of freedom, will give us MSTR and MSE. The F value comes from the ratio of these two values right here, MSTR over MSE, and that gives us our F value. And then we have to go to the table to get our P value, depending on the degrees of freedom, numerator and denominator, and the F value. All right? So that's the table. Once we get that table, we are able to answer the question whether or not at least one of the means differ, because we'll get the p-value, and that p-value can be compared to alpha, like we've been doing all along. Okay? So we have the formulas that we would use, and I think it's best at this point to kind of get into an actual example. So I'm going to go through one that's right here first, and then after that one, I will look at our next topic, which is called a two-way analysis of variance. If you have questions anytime, please feel free to ask me. All right. So now here's what we have. We want to compare the performance of three different types of waxes, I guess. And I'm not sure what we're measuring in this problem, but we have three types of wax: wax 1, wax 2, wax 3. So that's the treatment. Another thing you could actually, another example of that, and when we think of treatments, you know how when you buy gasoline for your car, there's regular, there's plus, and there's supreme. So we could think of treatments in that case where the octane level is different. So regular have one treatment level with a certain octane level. 2 have more octane, so that's another treatment. And 3 has more, even more octane, not 3, but supreme. And so one would expect the mileage performance to be different. So maybe we take a random sample of cars using regular and say, okay, fill up the tank and then see how far, or put a particular volume of gasoline. You don't want to fill up the tank because different tanks have different sizes, different cars have different tank sizes. So every car gets a, I don't know, say 30 liters of gasoline, and they drive until the car stops and see how many kilometers they actually drove. And then you would get that information. So now you could actually test which gasoline gives you the highest average distance travel, all right, per liter. And so in that case, we would have an experiment involving 3 different levels. It doesn't have to be just 3, it could be 4. We would need the sample mean for each of those. And remember, columns are J, rows are I. So essentially the sample means they are, let me change the color of my pen here. The sample means X bar J. The sample variances are S squared J. So how can you find the sample variances? By using the formulas that we learned back in chapter 3 for sample variance. All right? So if we have the sample variances, in some cases we will give it to you, some you have to calculate it. So once you have sample mean, sample variance, you could go about stating the problem. So the hypotheses will be written as follows. All the means are the same, or not all of them are the same. You don't try to put notation on that one. We just say not all of them are the same. Because then you'd have to say mu1 is not equal to mu2, or mu1 is not equal to mu3, or mu2 is not equal to mu3. That's too much. At least one of them is different, or they're not all the same. So that's what it is. The number of washes before the wax wears off, I guess. So the mean number of washes using type 1 wax, mean number of washes using type 2, type 3, etc. So is there a difference between those means? Now, we're going to need to calculate a couple of things. We need to calculate SSTR, SSE, SST, and all of those things. So what are the formulas for those? We need formulas for those things. So we will need X double bar, which is the overall mean for across all of the 3 different types of waxes. So we have to add up all of their values and divide by 3. We'll calculate SSTR, we'll calculate SSE, and then we'll find MS values and so on. So let's take a look at what those formulas look like again, just to remind ourselves. So the first thing we want, excuse me, is we will want SSTR, which basically means the sum of the treatments, sum of squares due to the treatments, which is essentially NJ X bar J minus X double bar squared. In other words, what is NJ? NJ is the size of the sample. And then X bar J is the mean for that treatment. X double bar is the overall. So X double bar is if we add up everything Xij and we divide by sample size n. In other words, we add up everything across the 3 groups and then we will get X double bar, all right? And then to get X bar, you will take each group independently and then average them to give you the sample means. So as you could see here, we get X double bar by taking the average of, you see we have the sample mean for column 1, column 2, column 3. If we average those 3, essentially we'll get the average of all of those numbers put together. If you want to, you could add them all up together, which is 5 by 3 is 15 values, and take the average and see what we come up with, all right? So that's not what I wanted. Okay, go back here. So we see the average of that is 29.8, that is X double bar. And then now we take each individual mean, subtract the 29.8 from it, square it, and then multiply it by 5. That's what you see in here is this formula of NJ X bar J minus X double bar squared, and we're adding it all up. So NJ, so for wax 1, N is 5. The average for wax 1 was 29, and the overall average is 29.8. We repeat that for wax 2 and wax 3. And then when we get SSTR, if we divide it by the degrees of freedom, which happens to be k minus 1, but k is 3, so 3 minus 1 is 2. So when we divide it by 5.2 by 2, we get 2.6. So that's MSTR. Now, SSE is the sum of the squares due to the error. I remember what we said that was. Well, that was going to be n minus 1, nj minus 1 times sj squared, and we add it all up. All right? So we were given those values. We were given the sample variances. We know the sample sizes, so therefore we could compute that. So there are 5 values in each column. So 5 minus 1 is 4. 4 times 2.5 was the variance for wax 1. 3.3 was the variance for wax 2. And 2.5 was the sample variance for wax 3. So we're using this formula right here. So 4, n minus 1. The 2.5 is the s squared. So now that we have the SSE, if we divide it by n minus k, so the degrees of freedom in this case is nt minus k. All right. The notes are in your text, and then I believe we passed it earlier. If we wanted to look, go back and see. We passed that information earlier. I probably didn't dwell on it, but the information is right here somewhere. See the degrees of freedom, nt minus k. All right. So once we have all of these values that we just calculated here, we have SSE, SSTR, MST, MSE. We could actually go ahead and develop the Anova table, right? Now, we want to do a test based on an alpha value of 5%. So we could use the critical value approach, or we could use the p-value approach. So if we use the critical value approach, our F critical is F.05, but remember we need degrees of freedom 1 and degrees of freedom 2. What's degrees of freedom 1? Degrees of freedom 1 is the number of columns minus 1, k minus 1, which is 3 minus 1, which is equal to 2. And degrees of freedom 2 is n minus k, which is 15 values minus 3, which is 12. All right? So in other words, F.05 to 12 gives us our critical value of 3.89. And that is what we will use as our critical value. So if our F statistic is larger than 3.89, we will reject the null hypothesis. Or if the p-value is less than 0.05, we will reject the null hypothesis. All right? So in case you want to see how I get that 3.89, why don't I take a look at that for you? So I'm going to stop sharing. I'm going to go back to the table so you can see it. All right? So we said our degrees of freedom was 2 and 12. So I got to look at 2. The numerator degrees of freedom is 2. Denominator degrees of freedom is 12. I am only looking at 5 right here, so I need to scroll. Let's see if I could find 12. So 2 12. So if we go 2, 12, I am down here. But remember the area in the tail, our alpha value is 5%. So this is 5% right here. And so 3.89 is what we're looking at as our critical value. When the area in the tail is 5% and the degrees of freedom is 2, 12, 3.89 is our critical value. I just saw my light flash a while ago, so if I get cut off, you know, then my power is gone. Okay. All right, so now that's how we would actually go ahead and find the critical value. Good. So we should try to summarize everything. We're seeing the calculations being done, but we should try to summarize everything right here using this Anova table. So sources of variation. So for the treatments, we found a sum of squares of 5.2. And for the error, it was 33.2. The degrees of freedom was 2 and 12. If we divide the 5.2 by 2, we get 2.6. We divide the 33 by 12, we get 2.77. We take the ratio of those two, we get 0.939. Now you can see 0.939 is kind of close to 1. Those, that basically suggests that MSTR is really not that different from MSE. 2.60 is not very different from 2.77. So in that case, we don't have strong evidence that those means differ. All right? In other words, the 3 different types of waxes are not giving us different amounts of car washes. They're more or less the same. So if a manufacturer is claiming, oh no, wax-free is much better than wax number 1, then you can say, I don't have the evidence to support that. Okay? All right. So that essentially is a question here that we could certainly do. Let me see if I have a question that I was able to pull up for you, another one. Okay, I'll go back for a second. All right, here's another one right here. We're testing for the equality of means. And then we have, again, 3 different plants. And what are we comparing? Let's see. Let's see what the problem context is. So here it is. Testing for the equality of K population means, an observational study. Reed Manufacturing is the name of the company. A simple random sample of 5 managers from each of 3 plants was taken, and the number of hours worked by each manager in the previous week was shown on the next slide. So the factor is the manufacturing plant. What are the treatments? The different locations, Buffalo, Pittsburgh, and Detroit. Who are the experimental units? The managers, the people that actually we collected the data from. And what's the response variable? What is it that we're measuring from them? The number of hours worked. So that's kind of what we're measuring from them. The data that we have is the 5 managers gave us for the Buffalo plant, 48, 54, 57, 54, 62, etc. Pittsburgh, we see the value 73, 63, 66. For Detroit, 51, 63, 61, 54. The idea is, do those managers kind of work all the same average number of hours, or are they different? All right. So I'm going to try to set this up and then compare so that you could see how I'm setting it up. So you could compare them, and then we'll compare the answers with what we have. So we'll assume that the mean number of hours are the same versus they are different. So let's start off with HO. HO? Mean number of hours, the same versus HA, mean number of hours differ. Cool? So if the mean number of hours are the same, then it means mu1, city number 1, is equal to mu city number 2 is equal to mu city number 3. I think we have Buffalo, Pittsburgh, and Detroit. So if we wanted to use that, we could say Buffalo, Pittsburgh, Detroit. They're the same, or at least one differ. At least one mean is different. I said the same thing, but I wrote it differently. Okay, so that's step 1. Step 2, test statistic. So the test statistic is just the ratio, is the F statistic, MSTR over MSE. The degrees of freedom, DF1, is K minus 1. The degrees of freedom 2 is NT minus K. So that's step 2 right here. All right? Step 3, the decision rule. So how do we know when we have enough evidence? Well, what we're going to have to do is to find a critical value, F critical, which is F alpha, degrees of freedom 1, degrees of freedom 2. I think alpha is 5%. Let's go back and double check. We were not told, were we? Yeah, read manufacturing. So Janet Reed would like to know if there's any significant difference in the mean number of hours worked per week for the department managers at her 3 manufacturing plants in Buffalo, Pittsburgh, and Detroit. F tests will be conducted at 5%. Okay? So let's find the critical value. So what we will need is, we need to find the degrees of freedom. So DF1, we said is K minus 1. We have 3 plants, so 3 minus 1 is 2. DF2 is NT minus K. But what's the total sample size? Total sample size, we have 5 in each. 5 3s are 15. All right? Pittsburgh, Detroit. So 15 minus 3 is 12. I think we're going to have the same critical value, 12, as before. So F.05 to 12, without going back to the table, happens to be the same as the last question we just talked about. Okay? Happens to be the same, the last one. So that's step 3. Step 4 and step 5, well, step 4 is where we have to develop the Anova Table. All right? Sorry. So we need to come up with an Anova Table. Step 4. But to do that, we need some analysis. We're going to need to calculate, so SSE, SSTR. Actually, let me put SSTR first, which we said was NJ x bar j minus x double bar squared, which means we're going to need x double bar, we're going to need the xj's, and we're going to need the nj's. So if we go back to our table, so if you're writing this down, those values here are our, say, sample mean, so those are x bar j's. Sample variances, those are s squared j's. The nj's happen to all be the same size, so nj is equal to 5 for all of them. And what else we need? We need now x double bar. X double bar is the average of those 15 values, but we could also get it by just taking the average of those 3 values. In other words, the average of the averages. So x double bar is 55 plus 58 plus 57 divided by 3, whatever that turns out to be. So 55 plus 68, and where's my calculator? I know I have one right here. Well, actually, I think I have the answer if I go forward. It turns out that it's 60. It's right here. So if you want to see the calculations, I mean, I could rewrite it as that I'm calculating x double bar by taking the average of the averages. So it is x double bar is equal to 55 plus 60 plus 57 over 3 gives us 60. And then we get the SSTR, right, by taking nj times x bar j minus x double bar, and we square that. And we do that for each of the 3 columns. When we do that, we get a total value of SSTR of 490. But when we divide it by the degrees of freedom, k minus 1, we get 245, right? K minus 1, which is 2, 245. So that will give us MSTR and SSTR, okay? Now we repeat the process to get, well, it's different actually, to get SSE and MSE. To get SSE, remember our formula said SSE is equal to nj minus 1 times sj squared. And we add that all together, SSE. So SSE, nj minus 1. So for the first column, j is 5. 5 minus 1 gives us 4. The sj squared, 26. That must have been squared already, the 26.5 and 24.5. So let's go and see. Let's make sure that the values were actually squared properly. Okay, so, oh yeah, we already calculated the sample variance, Sj squared. So that's already Sj squared, not S, but Sj squared. So you see the 26, 26.5, 24.5. So that explains, sorry. So we could see right here. So the first one, 26 times 4, 26.5 times 4, 24.5 times 4. Give us 308. But then if we divide 308 by 15 minus 3, which is 12, we get 25.667. And then now we could find the F value. So what to do here, once we start getting all of these values, is ready to put everything in the form of a table. So the table goes like this. So I'll actually do the table for you. The sources of variation, the sum of squares value, the degrees of freedom value, the MS mean square value, F value, and the P value. So it's kind of what we set up. Sources of variation is due to treatments. All right, the treatments. Then we have the error, and then we have the total. So what was it? I think it was 4. If we go back here, it was 490 was SSTR, and then 308. 490 and 308. So 490, 308. If we add up those two, we'll get the total. That's 898, 3 and 4, 7. 798 is the total. Degrees of freedom for treatments is k minus 1, which is 2, which is 3 minus 1, which is 2. And n minus k, 15 minus 3 is 12. Now, the MS value is obtained by dividing an MS, mean square, is a sum of squares over degrees of freedom. So I will have to divide the 490 by 2 to get my MS value, which I believe was 245 over here. 308 divided by 12, I could calculate it, but I happen to have it over here. 308 divided by 12 is 25.667. So we divide that 308 by 12, we divide that 490 by 2. Now to get the F value, you must divide the 245 by 25.6, which is 9.55 over here. You could use your calculator. 9.55. So if you recall, our F critical value is 3.89, which basically means that our F value is going to be larger than our critical value. In other words, it's overestimating that population variance significantly. So much so that the F value is 9.55 compared to 3.89. And so we reject the null hypothesis and conclude that the managers do not all work the same average number of hours. The managers don't work the same number of average hours. And so, how do I find the p-value in this case? Well, I know my degrees of freedom are 2 and 12, and I'm going to have to look for 9.55. So let's take a look at how we would find the p-value for this situation right here. Okay, I'm going to share. So I'm back to the table. Numerator degrees of freedom 2. 12 is the denominator degrees of freedom. And I'm looking for 9.55. So if I come down here, I want 9.55. What's the biggest value I have in that table? It is 6.7. Because it is 6.7, I have to keep going for me to get to 9.55. So notice what's happening to the area in the tail is going from 10%, 5%, 2.5%, 1%. So since 9.55 is bigger than 6.7, the area in the tail will be less than 1%. So if we keep going, what will be left will be less than 1%. So I will write my p-value. I will write my p-value as p-value as less than 0.01. Okay, so that's step 4. We now have the Anova table. And then we could do our conclusion. Conclusion, 5. So since 9.55 is greater than 3.89, reject HO. All right? And then what do we conclude? At least we conclude at least one mean is different. All right? At least one mean is different. Possibility of type 1 error. Okay. Possibility of type 1 error. And that concludes what we call one-way analysis of variance, one-way ANOVA, or completely randomized design. Completely randomized design. All right? So that means that the samples do not contain anything in common necessarily. They are randomly chosen and completely assigned. So essentially we took 15 managers, and the 15 managers are divided up between these 3 different plants. All right? Good, so that's that question. Now there is a technique for you to do the assignment. There's a question that you'll be asked. Which one is the one that differs? And there is a Fisher LSD procedure that we have to kind of just expose ourselves to. LSD, least significant difference procedure is called. And it's kind of similar to the Masculio procedure when we did chi-squared, except that that procedure was designed for proportions this procedure is designed for testing difference between means. All right. So that procedure essentially tests what it does. It actually does pairwise comparisons now. It does pairwise comparisons, and it calculates a t-value based on this formula right here. If we take any two treatments, I and j, then we'll look at the difference between the means I of I and j, and we'll divide by some kind of estimate of a standard error, 1 over ni plus 1 over nj, but we multiply by MSE. We treat MSE as if it is a variance, right? A pool sample variance. And so here's what you end up doing. You end up taking the difference, the absolute difference between those two, and then you're going to calculate the least squared, or least significant difference, sorry, by using this formula right here. Notice that we now have a t-value introduced in this. That t-value is kind of like as if we were finding a confidence interval. Essentially, is what this process is like finding a confidence interval for the difference between mu I and mu j, and then finding out whether or not we have sufficient evidence of a difference between I and j. So if that here, we will reject the null hypothesis. That means we'll conclude there is a difference between the two if we can show for that pair that the absolute difference is greater than or equal to the least significant difference. And you got to do this for all the combinations. So we just got to repeat that step and then compare that. And as soon as we find one that's different, then we conclude we will know which pair or which one is significantly different from the rest. Okay. So I will, that's the sort of Fisher procedure. You could get an example in MindTap on that. You could also get an example in the textbook on that procedure, the LSD procedure. Cool. So that is one-way ANOVA. That took us a little bit of time here, almost an hour and a half. We got to now do the second part of this lecture, which is two-way analysis of variance. So I'm not sure if you have any questions for me at this point. If you do have a question, please feel free to ask me right now. Otherwise, I'm going to do a quick review. Since we already are familiar with some of the terms, then it shouldn't take us too long to do two-way analysis of variance. It have a little extra calculation to do, but it's a similar kind of calculation. So if I'll just wait for a second to see if you have any questions. If not, I'll continue.
Yeah, on MindTap,
So while I'm waiting for you, if you have a question, I'm going to load up my next PowerPoint. Save and close.
I got a quick question. Hello?
We want to do this.
Hello?
So now we're going to do two-way analysis of variance. I'll stick with a blackboard. Then we're going to get a file. This is one of the coolest apps that I've ever used. It's called Explain Everything, and it's just great for teaching. I could actually record. I mean, I'm using Zoom to record what I'm doing, but if I just want to solve an example just on my iPad alone, that app allows me to record what I'm doing, and then I could create tutorials doing that. But it is a beautiful app. It came out first at $2 and something, and now they want a subscription for about a monthly subscription. Wow. So fortunately, you could actually buy it outright still and not have to pay subscription. If you want a subscription, you then could do things like sharing and collaborating, but I'm not interested in that. But this is actually one of the best apps that's been designed for folks teaching. Let's find the second part of my lecture here. And then I'm going to load it in, import it. And what that allows me to do is to bring in the PowerPoint. And once it loads up, I could then add pages in between the PowerPoint. So for example, as we go through, then I could say, okay, I'm going to insert a blank page and then use that page to write on. You know? We could go yellow perhaps. There we go, something like this. All right. So it is fascinating. It's fantastic. All right. So now let's go to
Dr. Miller.
Randomized block design. What is that all about? So in the first place, what we learned was randomized design, completely randomized design, where essentially we have the different treatments. For example, the gasoline, regular plus supreme, and we could take, say, I don't know, 30 cars and randomly assign 10 to each. Now remember, in a completely randomized design, they don't have to all have the same sample size. That's why we put NJ. So you could work with whatever the sample size. I could have 20 in one getting gas, one type of gas. I could have 5 and then 5, 25 and 5. Or I could have 18, 6, that's 24. And another, well, doesn't have to be equal. 18, 5, that's 23 and 7. So I could have different combinations, right? In the randomized block design, what we do now is that the elements on which we collect the data, in other words, the people or the cars or whatever, are used for each treatment. In other words, we repeat the experiment. So we often refer to that situation as randomized block design or ANOVA with repeated measures and so on, or two-way ANOVA. All of that, what do we mean by two-way ANOVA or repeated measures and so on? So I'll give you an example. Say we took 10 cars and we gave them plus fuel and we let it run out. After it runs out, then we give them regular and then that runs out. And then we give them supreme. So in a case like that, you are using the exact same cars in each situation. So you're repeating the experiment with the same car. I am having the same car drive with regular, then with plus, then with supreme. Now, of course, just in case the order in which you use the gasoline might affect the result, you will randomize that amongst the different cars. So another car might actually start with supreme, then go to plus, then go to regular. Then another one will start at plus, go to supreme, then regular. Another one start at plus, go to regular, then supreme. So you mix and match it. So you remove the element of the sequence having an effect on your results. One of the nice things about this particular design is that it is much more sensitive than completely randomized design. Why? Because what it does is that it, by using the same individuals, you are in essence eliminating the variation among individuals. In other words, you're accounting for that variation, not eliminating, but accounting for that variation by using the same people. So let's just use our example. If I use different individuals doing marketing, accounting, finance, and econ, and I see really good scores in econ, is it because econ was so much easier? Or maybe I happen to assign very bright people to econ? Who knows? I don't know. So in a case like that, it is possible that it could be the exam. It is possible that it could be people who actually wrote the exam. So there are multiple explanations for the variation that we see. How can we control for that? Have the same people write the econ exam, write the finance exam, write the accounting exam, write the marketing exam. So if you're using the same people, you are now accounting for the variation amongst the individuals, and then we call that blocking. So randomized block design. And not only that, now, because that same individual gave you a score for marketing, accounting, finance, and economics, we are repeating the experiment, hence the term repeated measures. So it is like paired difference tests, t-tests, when we were doing two samples that were paired. It is like that, but with multiple populations, with 3 or more populations. So basically, we're taking a paired difference test and we're adding additional populations to that. And that gives us a slightly more sensitive test. And also, too, because using the same individuals, you actually have a smaller sample that you need to worry about. In other words, I could get a random sample of 10 cars and use the same 10 cars over and over again. Whereas if I was using different cars, then I need 10 multiplied by 3, I need 30 cars to participate. All right? But each of them have their advantages and disadvantages. So in the case where it's completely randomized design, an advantage is that you don't have the effects from learning or sequences and so on. And if those things are not important, I mean, then maybe if those things are not that important, you could just do a randomized block design. But if they're important to you and you want to separate that out, you certainly can do a randomized design. Okay? In the case of the repeated measures, we could use the smaller sample size. We keep repeating them, so we don't incur high costs. Right? It is much more sensitive. It can detect whether or not the treatment is actually having an effect a lot better and faster. But of course, it has risk if there are order effects, learning effects, and that sort of stuff like that. So maybe the sequence within which you do marketing, finance, accounting, and so on affects your mark. If you do finance first and you didn't get a good mark, it might affect your marks in the others. So those things can be very important. All right. So randomized block design is just the situation, as I mentioned to you, where we are repeating the experiment using the very same individuals or elements and so forth. All right. Now, here's what happens. And I'll explain that to you. Maybe for diagram, it might be a little easier to explain it. All right. So let's see what happens. So in the first case, when we took the overall sum of squares, SST, total, what we did was we broke that down into the sum of squares due to the treatments, sum of squares due to the error, and then we used those two things with your k minus 1 or your nt minus k to give us an estimate for sigma, right? That's what we did, give us an estimate for sigma. So in a case like that, remember that if we get those two variances to be similar, this is a MSTR, MSE. If they're not very different, then we don't reject the null hypothesis. But if they're very different, then we reject the null hypothesis. What happens now is that if we decide to use blocking, where we repeat the experiment, we could now divide this up into 3 parts. We now have what we will call sum of squares due to blocks, SSBL. So we'll add a 3rd part, and that the number of the blocks the number of blocks would be b minus 1 and we'll call this MSBL. All right. So now, if we wanted to compare, so this allows us to determine whether or not the treatment means are the same when we compare MSTR to MSE. But if we compare MSBL to MSE, this is a different variance we're going to be comparing it to. Let's just call this one 1 and 2. So now we're going to compare that. We are basically now estimating the variance across the blocks. All right, the blocks across the blocks. Now this is not making any sense right now because all you see is a bunch of symbols. So let me try to get it to make a little sense to you. So let's go back to our gasoline example. Regular plus and supreme. I'm assuming all of you drive and you know what those things are. So if I took 10 cars.
May I interrupt for just a moment?
1, 2, 3, 10 cars. And I use the same 10 cars right? The same 10 cars over and over again. Then these are my treatments right there, the gasoline treatments. The number of treatments is K, which is 3. But then now I will refer to each row as a block. So how many blocks do I have? B in this case is equal to 10. I have 3 treatments and 10 blocks. All right? And remember, I am repeating the experiment. So there is variation among the treatments, right? But there's also variation among the blocks. So now what we do is we take the total variation, which is SST, and we now could break it down into SSTR due to the treatments, SSBL due to the blocks. In other words, the cars are not all the same. You could have a Volkswagen, a Hyundai, a Toyota, and so on. So there could be 10 different types of cars there. And with those types of cars, there's some variation amongst them. So that's where the SSBL comes in, blocks, sum of squares due to blocks. And what's left, we call it SSE, the unexplained part. All right? So we got to figure out how to get this and how to get that value right here. Now we already know some parts of this. All we need now is SSBL really. So what do we already know? Let's change the color. We already know that SST is equal to Xij X double bar squared. Add it all up, Xij. So if I do this over all of the values, in other words, I'm finding the sum of squares as if I were going to find the variance of all the numbers. So that's the formula that we would use. SSTR for treatments, you may recall, was NJ X bar J X double bar squared. And we add it all up over J. Now, what is NJ? NJ is the size, the sample size for column J. Column J would be regular plus or supreme. But notice in this question, because we're using a block design, the same number of cars is being used for each of them. So the sample size is fixed. So NJ is just B, the number of blocks that we have. In other words, the number of cars that are going to do the regular tests, that's going to use regular gasoline, is B, 10. Number that's going to use plus is B, 10. The number that's going to use supreme is also B, 10. All right? So that here tells you that we could replace NJ by B. So if I could replace NJ by B, all right, the number of blocks. I could do the same thing now for treatments. Not treatments, sorry, blocks, SSBL. All I do is I just turn it on the side, and then it becomes, so now basically a block is a row. I'm going to do this for each row. I'm going to call it x bar I minus x bar squared. But how many values do I have in each row? K, the number of treatments. In other words, the size of a block is the number of treatments that I have, which is 3 types of gasoline. So for car number 1, 3 types of gasoline. Car number 2, 3 types of gasoline. Car number 3, 3 types of gasoline. So in that case here, we have, we are going to replace NI by simply putting K. The same way we have B for the other one, looking at treatments, we put K, number of treatments, when we're looking at blocks. And then it turns out that the degrees of freedom here for everything is still n minus 1. The degrees of freedom in this case would be for blocks k minus 1. For this one, degrees of freedom would be b minus 1, right? Number of blocks that we have. And for the SSE, and the formula for that one is can be a little crazy. I don't think we need to Xij, actually put that in here. So it is Xij minus x bar I minus x bar j plus x double bar squared, something like that. You don't have to actually remember that. I'll tell you why. Because if you calculate this value, which is easier, this value and this value, we could find SSE by simply subtracting those 2 values right here from SST, and we get SSE. So we don't actually have to do the explicit SSE calculation, all right? The degrees of freedom in this case for SSE is k minus 1 times b minus 1. That's the degrees of freedom. So once we could calculate those, we just set up the Anova table just like we did before, and we could do the tests, all right? So that's, I'm just going to sort of review that with you and then see what happens, all right? So you can see what the Anova table will look like. It looks very similar to what we had before, just as an additional row. That's all that we've done, is add an additional row. So for treatments, SSTR, K minus 1. For blocks, SSBL, B minus 1. For error, SSE, which is what's left, K minus 1, B minus 1. When you add them all together, you get the NT minus 1. Now, remember, an MS, a mean square, is a sum of square over degrees of freedom. So therefore, if I divide SSTR by K minus 1, I will get MSTR. And then SSBL by B minus 1, I will get MSBL. And then MSE. To get my F value, it will be MSTR over MSE, just like before. But now it's a lot more precise, it's a little sharper. We could actually calculate a secondary F value by taking MSBL over MSE. And you could ask me, well, why would we need to know this? Why would we need this situation? Well, that's if we wanted to test are the mean mileage for the cars different, for example. So in the example I just did over here, the treatments were the types of gasoline. So I am asking whether the mean performance for the different gasolines are the same. So that's the usual test that we do. But what if I wanted to ask you the question, is the mean performance for the cars the same? Then that's when I would need this second F value right here. Okay, but most cases when we set up those experiments, we are only interested in the difference between the treatment means. But if you are interested in the difference between the block means, you could also examine that as well. All right. So that's the essence of that problem. And then let's see how we can set it up. So let's read this example right there. Crescent Oil Company. Crescent Oil has developed 3 blends of gasoline. Now notice they like to use 3. And I think it's because when you do 4, you have more work, 5, you have more work. But I just want you to know that you don't have to be restricted to 3. It can be more than 3. So Crescent Oil has developed 3 new blends of gasoline and must decide which blend or blends to produce and distribute. A study of the miles per gallon ratings of the 3 blends is being conducted to determine if the mean ratings are the same for the 3 blends. Interesting. Those 3 blends could be your regular, plus, and supreme. Same basic idea that we were discussing. They just call them blend X, which could be, we could change it to plus, regular, blend Y, plus, and blend Z, supreme. And then the blocks are the automobiles. So I guess we've already kind of gone through the context here. So we have 5 cars are being used, and clearly in this case, with the 5 cars that are being used, we are repeating the experiment with each of the 5 cars. We're giving each of them blend X, then each of them blend Y, each of them blend Z. So that's the 3 situations. But remember, we're using the same cars in each of them. We're going to need the block means, which you see here. And then we're going to need the treatment means. All right? And then, of course, we're going to need X double bar. And then we're going to need the find the sum of squares for those 5 by 3, 15 values. We're going to have to find the sum of squares for that. So SSTR, as you could see, is the same basic formula that was applied earlier. In this case, 5. 5 happens to be the number of cars, so that's the number of blocks. B times the column average, which is like for blend 1, blend 2, blend X, blend Y, blend Z, and so on. So that's what we're finding here. And once we find that, if we then divide the SSTR by the degrees of freedom, we get an MSTR of 2.6, all right? Mean squared due to blocks. So mean squared due to blocks, now when we do the calculations, kind of similar to SSTR, but you're going to get SSBL, but now we're looking at the means for each of the cars. In other words, the block means. We're going to do this for 5 times because we have 5 cars. We get 51.33, and we get a 12.8. Now we'll find SSE by subtracting. Let's see what we have here. We will need to find SST and subtract the SSTR and SSBL from it. So how do we find SST? To find SST, you'd have to do this. SST is equal to the sum of Xij X double bar squared. So in other words, we have to find the overall mean, subtract that overall mean from each of the 15 values and square them and add them up. And we will get 62. All right, SXT 62. And in the end, we get an SSE of 5.47 when we divide it by the degrees of freedom, which is basically K minus 1 times B minus 1, we get 0.68. Now, if we look, we set up our Anova table. The treatment, source of variation due to treatment, so SSTR, SSBL, SSE, SST. SST, SSE, SSBL, SSTR, right? And then here are the degrees of freedom. If we divide these values, we'll get the mean square. And then if I divide the 2.6 by 0.68, I will get the MSTR. If I were to divide the 12.8 by 0.68, I will get the MSBL. Let's just see what that is. 12.8 divided by 0.68. 18.82. That seems like a pretty big F value. 18.82, which even without the p-value is telling me that chances are those cars are not the same kind of cars. There's a difference among the cars. Now with 3.82, it all depends on what our critical value is. And I suspect our critical value, we're using 5. And then our degrees of freedom are, we have 3 and 5. So our degrees of freedom turns out to be k minus 1, which is 3 minus 1, which is 2. But then the degrees of freedom for SSE is k minus 1, b minus 1. That's basically 3 minus 1 times 5 minus 1, which would be 2 minus 4, 2 times 4, which is 8. All right? So 2 times 4, which is 8. And so in that case, we would find the F value based on 0.0528, which is 4.46. So that's our critical value. As you could see, the 3.82, which is what we got, is not greater than, I shouldn't write it this way. I think there's a way to write this. It's not greater than 4.46. We will fail to reject HR. So we have insufficient evidence that the 3 types of gasolines actually differ. So 3.82, 4.46. So as you could see, the p-value is actually greater than 5%. And the 3.82 is smaller than 4.46. We cannot reject HL. There is insufficient evidence to conclude that miles per gallon ratings differ for the 3 gasoline blends. So they cannot go ahead and try to sell that to anyone and tell them, hey, those 3 types of gasolines differ. It will not be accurate. Good. So that basically is 2 analysis of variance. I had this other question right here that you could attempt. It actually came out of your text. I'm going to, I believe, let me see, do I have the solution to that here? I didn't, oh, I did post the solution. So I'm going to just have it recorded, and then that way you could check it out when you go to see, when you watch, if you're rewatching this video. So essentially what we want to check here is whether or not the scores, this is from a sort of what you call like an SAT test, right? SATs. And we wanted to find out whether or not the mean score for reading, mathematics, and writing are the same or do they differ. So we actually looked at 6 students who did SATs and actually look at their scores. So you notice now, since we are taking the scores from the 6 students, student number 1 gave us all these 3 values. Student number 2 gave us all these 3 values and so on, which basically means we have a block design. So our treatments are reading, mathematics, and writing. And our blocks are the 6 students. So these are our blocks. And these are our treatments. So what we will need to do is to get your treatment means, your X bar J's, and put them here. And then get your block means, which is your X bar I, and put them here. So average those three values, put them here. Average those three values, put them here. Those three, put them here. Those three, etc. Right? Then average those 6 values, put that here. 6 values, put that here. 6 values, put that here. That will give you your treatment means. And then with that information, we could go ahead and, we must find the overall X double bar, which is basically taking 6 times 3, the 18 values, the sum of Xij over n is 18, and is 18 values, all right? Your number of blocks you have is 6 students, and your number of treatments, K, is 3. So you know that you'll have 6 minus 1, 3 minus 1. So you have different degrees of freedom, and then you'll have K minus 1 times B minus 1, which is 3 minus 1 times 6 minus 1, which is 5 times 2, 10. So we will need that information. And then you just repeat what was done earlier. So you could see here, if I were to so I have the treatment means, so I calculate the X bar for each of the treatments, and that's that here. Then take the block means, there's 6 cars, so here's the mileage for each, no, sorry, not cars, individuals, students. Here's their scores, the overall X double bar, and then we will calculate SST overall for the 18 values. And as you can see, we got that here. Then we calculate SSTR for the treatments. So here, and then SSBL. SSE will find from subtracting SSTR and SSBL from SST. It gave us 1200. And then we put the Anova table together. And what do we see? We get a value for treatments 5.62. Question is whether or not that is larger than the critical value. Let me see. Do we have a critical value? Yep, the critical value turns out to be, well, let me see here. No, using Excel, we need to have p-value. Oh, we have a p-value, sorry. So if we're doing the p-value approach, you could use Excel, you get 0.0231, or if you use the table, you will get between 0.01 and 0.025. If we are testing at alpha is equal to 0.05, then we will reject the null hypothesis and conclude that the tests are not, and the test scores, the average test scores for reading, writing, and mathematics are not the same. Okay, I believe that's the last slide. So there you go. So you could see that. So just to summarize, we just covered the randomized block design, and the idea behind randomized block design is that it allows us to control for sources of variation other than the treatments. So for example, by using the same students, right? By using the same students, we're able to identify that if there's a difference in the scores for reading, mathematics, and writing, it has to do with those subject areas, not the students, because we use the same students. If we use different students now, it could be because of our allocation of students to these different topics. And that makes, that could actually impact our results, all right? So that's analysis of variance. The only way to get through this is to actually practice it. So look at what I've done and then attempt it. It does have a few calculations you got to do in Excel. With MindTap, what MindTap tends to do, I noticed, is that it will give you a partial table. It will give you a table that you need to complete. And so if, for example, in randomized block design, you know the total sum of squares, you know SSBL and SSTR, then you just sort of add SSTL and TR and SSBL, and you subtract it from SST, and you'll get the SSE. Then based on the samples that you're given, you'll be able to calculate your degrees of freedom. And then you simply fill out the Anova Table. So essentially, the questions in MindTap tend to give you to fill out the Anova Table, but you got to know something about the relationship between the various parts. All right, good. So on that note, I did say that if anybody had any specific questions about something else earlier, that they could let me know. I was hoping to do office hours on Thursday of last week, but something came up and I couldn't make it. So I will spend a couple more minutes here if you guys have any questions. I know it's tough to do this after 2 hours of this heavy stuff. We come into the end. We just have regression to do, and then that is our last topic, regression, which typically I would say we could cover in 2 more or 2 maximum 3 sessions. So we should be able to cover regression in the next 2 sessions and then have the 3rd session that's left as a review, okay? So if you have any questions, you can fire away. If not, I'm going to post this video because I recorded it, and then that way you have a chance to go back and look at it again. Cool? Any questions, folks? Ken?
Are you hearing us? Do you hear us?
I'm not hearing you. I'm not hearing you, Ken. And I think you're speaking, but I'm not hearing you.
Yeah, I'm speaking, but
Let me just double check, make sure my sound output, internal speakers, yes. Speaker. I see what. Just wait, hold a second, please. Let me see. Human system, built-in output. Okay. Okay, Ken, go ahead, please. Sorry,
yeah, no,
my setting was off.
Can you hear me now?
Yes, I can hear you now.
Okay, I don't have any questions actually. I have to run away, so I'm out of time. So
no problem. But what I'm going, let me see here. I don't want to make a promise for Thursday because I'm actually supposed to head down to New Glasgow on Thursday, and I'm not sure I'll be able to have office hours on Thursday. I know that someone was asking about I think it might have been James. James has already left. There was a question, but I will respond to him via email. But if you have a question that you want to fire off via email, I know I do sometimes. I'm able to respond right away. Sometimes it takes a couple of days to respond, but I try to respond to you as soon as possible.
Yeah, so okay. I don't have any questions, so I just got to I got to take off.
No problem. Thank you very much. I'm about to shut down anyway. So Catherine, I don't know if you had any questions.
No, thank you. I'm good.
Okay, then. Thanks a lot. It was a long session, and typically the 2 toughest topics, Anova And regression, although I think regression is a little easier because most people are familiar with straight line concept from high school. But ANOVA, I think, is the toughest of them all. So if you could get through ANOVA and you could practice a couple of those problems, I think you guys will be okay. All right?
Perfect. Thank you.
Thanks. Good night.
I'll post that video as soon as it's processed. Okay, then. Take care. Good night. All right.